Hi, it's Mr. Ray with our next lesson in grade 12 advanced functions. We're in the rational units function. Sorry, we are in the rational functions unit. And today we're going to be looking at solving rational equations and inequalities. Now you've already done the polynomial unit where you solve polynomial equations and inequalities. There's a lot of similarities to what we did for that and for this, especially some of the techniques we use for the inequalities you will be seeing again here. So just remember, solving an equation means that there's an equal sign between two sides. One or both of those sides will be rational expressions. And an inequality, you'll have an inequality sign, less than, greater than, less than, equal to, greater than, equal to, between the two sides. One or both of those sides could be rational expressions. Okay, so rational function, you should know the definition by now. Both numerator and denominator are polynomial expressions. Now, this is a new thing, critical point, and we're going to be using this for the inequalities. So basically, we're looking for the vertical asymptotes or zeros. Okay, and we'll get more into that later, but and this is a term also used when in the calculus course. We use this term quite a bit, critical points. So when I refer to that, it means basically zeros and vertical asymptotes. Something that makes the numerator 0 and something that makes the denominator 0. Okay, now I'm not going to go through this too much in terms of the key concepts. We're going to be factoring sometimes we'll be expanding. Usually the main objective before we start using our techniques is to rearrange the equation so that you have a 0 on one side of the equation or inequality, and then we go from there. So sometimes most of the work is getting the function in the right form so that you have a 0 on one side. Sometimes you're given the equation or inequality and the 0 is already there, so you don't have to do that work. So let's go from there. I think let's just dive right into it. I've got two examples of solving rational equations and two examples of solving rational inequalities, and hopefully that's enough to get you going for your homework and practicing some of the questions. Okay, so the first one here, and you can read the key concepts at your will. It's probably better to do the examples first and then go back to remind yourself from up here. So we have a rational expression equal to 4 over 3x minus 5 equals 4. So the first thing we're going to do is rearrange it. So when I have, a term equals another term, well, I can just subtract one term from both sides to get a 0. So I'm going to subtract the 4 from both sides. So I have 4 over 3x minus 5, and then subtract 4 equals 0. Okay, so I've got my first objective, get a 0 here. Now what I want to do is I don't want two terms here. I want one rational expression equal to 0, and then we're pretty set to go from there. So if I want to combine these two terms together, they have to have the same denominator, which will be 3x minus 5. So if I want to turn this into something over 3x minus 5, that means I have to multiply the 4 with 3x minus 5. And then I could put a 3x minus 5 on the bottom and then combine everything. Okay, so I'm going to do that now. So I'm going to make one expression over 3x minus 5. So I've got my 4 here, and then I'm subtracting 4 times 3x, which is subtract 12x. Then I'm subtracting negative 5, which is adding 5, equals 0. Now I can simplify. Sorry, that's not 5. That's 20. So negative 4 times negative 5 is positive 20. Okay, so I can combine the 4 and the 20. So I'm going to get a 24 minus 12x over 3x minus 5 equals 0. Okay, so now we've arrived where we basically changed this into a rational expression equal to 0. So here's my new rational expression. So the rational equations, once we get it in this form, are fairly straightforward, because if I want this whole thing to equal 0, it means the top must be 0. So I can go ahead and set that. 24 minus 12x equals 0. That means 24 equals 12x, or x equals 2. Okay, so we've got our answer of x equals 2, so we're basically done. One thing I would like to note, and it's always a good idea, when you look at your original equation, find the values of x that will make this undefined. And that basically means if this denominator was 0, we'd have a problem. So I can definitely say 3x, if I set 3x minus 5 equal to 0, that means x would be 5/3. So that means x cannot equal 5/3, because that would cause a problem here. Okay, so that doesn't tell us what the answer is, and we could have done that right at the beginning. Okay, now what's the point of that? That doesn't tell us what the answer is, but it tells us what it can't be, for sure. So it's always a good idea to have that and then compare it to what the answer you got. Now, in probably 99% of the cases, this number won't be the same as that, but there's a chance that you might get several solutions, several possible answers, and maybe one of those is 5/3. And if you go back here and say, well, wait a minute, x wasn't allowed to be 5/3, so at that point you would remove any of these restrictions on x that you saw at the beginning, which may or may not still be there. Okay, so that's always a good idea to do that. Most of the time you'll get the right answer without even thinking about that, but there's sometimes where one of your possible final answers was one of the restricted values. So at that point you'd remove it from possible answers. For this type of form here, there is another way of doing this, and it's probably a way you could have done, back in grade 9. Just think about 3x minus 5 equals 4. Well, I could make the 4 a 4 over 1. Now I think one thing you could do is, well, these are both the same on the top, so these have to be the same. You could set those equal, but that's a rare situation. But if you have basically a rational expression equals a number, you could do your cross multiply here. So that would be 4 times 1, 4 is equal to 4 times 3x minus 5. So 4 is equal to 12x minus 20. And add 20 to both sides, we get 24 equals 12x, and therefore x equals 2. So the same answer. Now you can't, this technique only works for certain situations like the one we have here, whereas this technique or process is kind of the one you're going to do most of the time, because you're going to have very different situations with the equation you're given. So this is the more tried and true technique. This is a technique that will sometimes work for certain situations. So, okay, let's try another solving a rational equation. This time it's obviously a bit more involved here. We've got rational expressions on both sides. We've got quadratics on the denominators, linears on the top. Okay, so the first thing I want to do here, even before I think about factoring, I'm going to make this equation equal to 0 by subtracting one of the sides from both sides. And it doesn't really matter which way you go, it'll still work. I'll keep the left side as it is and subtract this from both sides. So that would look like this: x minus 5. Now while we're doing this, I'm going to put my subtraction here, 3x plus 2 equals 0. Now just to save a step here, maybe I could factor the bottoms. So the quadratic on the bottom here, x squared minus 3x minus 4, that factors into x minus 4x plus 1. And this is a difference of squares that factors into x plus 1, x minus 1. Let's stretch this out a bit. Okay, and now the goal would be to combine these into one term. You can see we've got a bunch of factors on the bottom. So if you remember this process when we did rational expressions in grade 11, we want to have a common denominator since we're adding or subtracting, in this case subtracting. So I'm just going to make a note here of our greatest common factor. So that's going to be, so I'm going to have an x minus 4, an x plus 1, and an x minus 1. So basically that's kind of my instructions. I need to make both of these denominators into this because this is the collection of all the different factors on the bottom. So when I do that, okay, so I'm going to have my x minus 4, x plus 1, x minus 1. So you can see the one that's missing here is the x minus 1. So I'm going to multiply the top and the bottom. I've already multiplied the bottom by x minus 1. So I have to multiply the top by x minus 1 as well. So basically I've taken this rational expression, multiplied the top and bottom by x minus 1. Okay, and I'll do that expanded on the next step. For this expression here, you can see I'm missing the x minus 4. So I'll put all three that I needed, x plus 1, x minus 1. So there's all three of them. So what's missing is x minus 4, which I've already multiplied the bottom by. So I have to multiply the top by x minus 4 as well. And then that whole thing is equal to 0. Now I'm going to actually combine them into one expression. So on the bottom I just have my regular factors, x minus 4, x plus 1, x minus 1. Now I'm going to work this out. So that's going to be x squared. I've got a minus 5x and a minus 1x. So that's minus 6x. Negative 5 times negative 1 is plus 5. And then I'm going to subtract the result of this. Okay, I'm going to put it in brackets so I don't get mixed up with my subtraction here. So that's going to be 3x squared. I'm going to have a minus 12x plus 2x, so that's minus 10x. And then 2 times negative 4 is negative 8. And that's equal to 0 still. Okay, so I'm going to simplify the top. So I've got an x squared minus 3x squared. So that's a minus 2x squared. I have a minus 6x minus negative 10x, so that's plus 10x. Minus 6x, that's plus 4x. And then a 5 subtract negative 8, so that's 5 plus 8, it's plus 13. Now on the bottom, you're going to see in the next step, we really don't need to expand the bottom, so I'm just going to leave it the way it is, as factored. Now, okay, so now we've got it just where we want it. We've basically got a rational expression equals 0. So whenever we have this, that means that just like the last example, I want this numerator equal to 0. It doesn't, and at this point, it doesn't really matter what the denominator is, but it's worth stating at this point, just like we did in our last example, that x cannot be 4, negative 1, and positive 1. Okay, and the reason for that is the same. I may get an answer on the top that's one of these, and that can't happen. So I'm just keeping track of values that'll cause this function to be undefined, or this equation to be undefined. So so I'm just going to rewrite it as the numerator equal to 0, because we want the numerator to equal 0. So at this point, the denominator is not needed, other than to note the restrictions. Okay, now anytime I see a negative sign for the x squared, I basically multiply both sides by -1, just for better factoring. So basically all the signs flip. 0 stays as 0. And when we look at this, we see that this is actually not factorable, which does happen. That doesn't mean there's no answers. That just means it's not factorable. So what we do is use the quadratic equation. Sorry, not quadratic equation, quadratic formula. Okay, now, so I'm going to take this and show the results of that. When I'm not going to show the quadratic formula, but I would get x is equal to 2 plus or minus root 30 over 2. Okay, now these are the two answers, and these are the exact values. Okay, so if you're asked for exact solutions, this is what you would give. If you're asked to round your solution to the whatever decimals, you could actually evaluate both of these, and we would get x is approximately 3.74 and -1.74. That would be rounding to 2 decimal places. Okay, and if we just take a peek back at what x can't be, these solutions are not don't include any of those values, so we don't have to worry about excluding any of those. Okay, so that's how we would do this. Normally, a lot of times this would be factorable, and you'd set each factor to 0 to find the possible solutions. Okay, so that's solving rational equations, 2 examples. Very typical types of questions, but the process is there. Basically, always change your equation so you have a 0 on one side, and then on the other side, the non-zero side, if you have multiple terms, combine them together into one term. Once you have one rational expression equals 0, the numerator of that rational expression is equal to 0, and you solve for that. Okay, so let's do a couple of examples of solving inequalities of rational situations. Okay, so the first one, and this one looks pretty straightforward. We're gonna use the technique that we will use for all of these. You might just plug some numbers in and see what works and what doesn't, but that may work for some of these simpler ones, but the more complex ones, you want to follow the procedure that I'm going to talk about here. So first thing I'm going to do is, just like solving equations, I want that to be a 0 on one side. So it makes more sense to subtract 10 from both sides rather than subtract the rational expression. So 2 over x minus 5 minus 10 is less than 0. And remember the rules about these working with these inequalities. The sign always stays with that direction unless you multiply something or divide both sides. Multiply or divide by a negative number, then you flip the sign to the other direction. So if you're just adding or subtracting, you don't have to worry about that. Okay, so we've got the 0 on one side of the inequality, so that's good. But now what we want to do is combine these two terms into one term. So again, I've only got one rational expression with an x minus 5. So when I combine, it basically means my denominator will be x minus 5. So I'm going to have to multiply the top and bottom of negative 10 over 1 by x minus 5. So that's going to be 2 minus 10 times x minus 5 is less than 0. Okay, when I expand and simplify this, well, first let's expand. So 2 minus 10x plus 50 over x minus 5 is less than 0. And I can add the 50 and the 2 together, so I get 52 minus 10x over x minus 5. So this is a true rational expression now. Okay. Now, if this was an equation, if that was equal, I just set this equal to 0 and solve, but it's less than, so it's more complicated. So the first thing I'm going to do, once I get it as a rational expression with an inequality sign and then a 0, the next thing I'm going to do up here is find the critical points. We talked about that at the beginning of the lesson. So the critical points are basically two types of points: vertical asymptotes. Now I can go back to here and look at this equation. I find the vertical asymptotes by finding where the denominator is equal to 0. I could do that here or here, but basically at x equals 5, I'm going to have a vertical asymptote. Okay. I also find the zeros. Now it's pretty hard to find the zeros up here. Okay, but once we've got it in this form, the zeros are found by setting the numerator equal to 0 and solving. Okay, so it's really good just to forget about the critical points until you get here, and then you see, oh, look at that, I've got I can find my vertical asymptotes by setting denominator equal to 0. I can find my zeros by setting the numerator to 0. So basically 52 minus 10x equals 0. 10x equals 52, so x equals 5.2 is my one and only 0. If you plug that back into here, you'll see you get a 0 on the top. Okay, so I've got my two critical points. So what do I do with those? Well, this is where we're going to use our number line. And it might be overkill for this question because it's a linear over linear. But if you have multiple factors on the top and bottom, multiple zeros, multiple vertical asymptotes, it gets very tricky with the different cases. So this is a technique that we use for polynomials. Polynomials, we only looked at the zeros, but now we're looking at vertical asymptotes when we look at the rational functions. Okay, so we're going to do our number line. Always start off with our number line, and I'm going to place all my vertical asymptotes and my zeros. Well, these are really close together. I can space them apart just for visual effect, so they're not too close together. So I have I'll put a 5.0 and a 5.2 just to make it super clear. Maybe an X there for the x-axis. Okay, now you can see, and I can make this a little bit clearer on the number line. I know I have a vertical asymptote here, so I'm actually going to do like a dashed line so I can see that a little clearer. And the 5.2 is a 0. I know if I was to graph the function, it would cross the x-axis here. So the reason why these critical points are used is because I want to know, if I go back to the original inequality, when is this function less than 0? So in other words, when it is going to be below the x-axis. And you can see the critical points define the intervals that I need to test now. So I have interval here, interval between the two values, and interval greater than 5.2. So for each interval, I'm going to determine a test value. So anything less than 5, I always pick 0 if I can, because it makes the calculation easy. So 0 for this interval, This one's a little trickier because it's very narrow compared to the other regions. Something between 5 and 5.2. Well, let's do 5.1. And over here, let's make this a little more defined here. This region would be something bigger than 5, so let's make it 6. Okay, so what I'm going to do now I don't care about the actual, number value for each of these test cases. What I do care about is the sign. Is it positive or negative when x equals 0, and so on, okay? So all I care about is the sign. So I'm going to set up fractions for both of these. All I'm going to put on the top and bottom is the numerator positive or negative, is the denominator positive or negative when I put in this value of x. Okay, so I'll go down to this version, plug in an x equals 0. Well, the top is definitely positive. If I put an x equals 0 on the bottom, top is definitely negative. So overall, that interval is negative. Positive over negative is negative. Okay, for x equals 5.1, I'm going to plug 5.1 on the numerator. That gives me 52 minus 51, so that's still positive. And the bottom, 5.1 minus 5, that's positive too. So positive over positive. Everything, my function in between these two values is always going to be positive. And then x equals 6 as my last test case. I plug in x equals 6. Well, the top's going to be negative now, and the bottom's going to be positive. So overall, that region will be negative. Okay, so I've done my interval checks, and I've got my table all set up, or my line graph, line bar all set up nice. So now at this point I go back to the equation because it's an inequality. There could be multiple different things I do at this point. So I check the value here. The inequality is less than 0, so I'm looking for negative values along this number line. So negative values. And the other thing, it's just less than 0. It doesn't include 0. Okay, so remember 5 is a vertical asymptote, so it's never going to include a vertical asymptote, but every value to the left of that will be negative, as I just determined. So there's part of my solution. The positive part, definitely not part of it, because I'm looking for negative values. And to the left of 5.2, well, remember 5.2 is a 0, but I don't want the zeros. I just want less than 0. So I put a open circle there. And then everything to the right of 5.2, everything greater than 5.2 is going to be negative. So I'll shade that in just for visual effect. So there's my kind of solution using the number line, but I always like to use interval notation. So my conclusion is therefore x is an element of, so basically from negative infinity up to 5, but not including 5, and so 5.2 but not, so above 5.2 but not including 5.2, up to positive infinity. So there's my solution. Hopefully you remember at this point how this interval, the line number, creating your intervals and your interval testing gives you a nice easy solution. One of the other options is to look at all the cases, but I just find that so complicated, and this is so much easier to see what's going on. So let's, if I was to graph this, you could see that everything here is negative, and this is a vertical asymptote. So I definitely know I'm going to have something that goes down here. I was thinking about my graph. This is positive, so I probably have like a something coming down from positive infinity, and then crossing at 5.2 where I have a 0, and then to the left of 5.2 the graph would go below. Okay, so that's how that works. So you don't have to graph it. I'm just saying that you could use this to kind of visualize what the graph looks like. Okay, so let's do our last example. And when you see this example, it actually looks more complicated than the one we just did, but it's actually, well, part of it is much easier. I basically got to solve this rational inequality. This time it's quadratic over quadratic is greater than or equal to 0. Okay. Now the good news is we've already got our 0 here, so we don't have to be moving things around, rearranging, and then turn the other side into a single rational expression. It's already done for us. So at this point, all we have to do is factor the top and bottom. And they're both factorable, so we have x minus 2, x plus 1 on the top, and x plus 4, x minus 3 on the bottom. And that whole thing is greater than or equal to 0. Okay, and we don't have to do anything more. We've got everything we need. So before I do my number line and my intervals, let's determine the critical points, because we need those to determine our intervals. So the vertical asymptotes, remember I get those from the denominator. So the values that make the denominator 0 are -4 and +3. So those are my vertical asymptotes. The zeros, or x-intercepts, definitely call them that if you want, is when the numerator equals 0. So that will be at -1 and +2. Okay, so these 4 critical points. This will be definitely more complicated for the number line part, because instead of just having 2 critical points like we did with example 3, I've now got 4. But you'll see it's same method, just a little bit more work. So if I look, I've got -4, -1, 2, and 3. The spacing isn't all that important. You can see my 2 and 3 should be close together, but I'll leave it like this. Okay, so these are my possible x values. I know my vertical asymptotes are at -4 and 3. These 2 points are zeros. Now, I can kind of look ahead at my solution here, because this tells me the zeros will be part of the solution. Greater than or equal to means I want the zeros as well. So I can actually, right now, I can actually include these as part of the solution, because the zeros are part of the solution, greater than or equal to. Okay, so now I've got 1, 2, 3, 4, 5 intervals. So I'm going to set my test values. Again, x equals, I get, most of these are pretty arbitrary. X equals -5 for less than -4. The next one could be x equals -2, something between -4 and -1. I'm going to use 0 here for between -1 and 2. This one's a bit more restrictive. Between 2 and 3 is 2.5, and bigger than 3 I'll use x equals 4. Okay, so again, all I'm going to do here is determine the overall sign of the function at these test values. I'm going to look at the numerator separately and then the denominator, just to simplify the work a bit. So if I plug in -5, I get negative on the top, so that's positive. I get negative on the bottom, that's also positive. So overall, the function is positive for this interval. If I plug in -2, I get negative on the top, which is positive. I get positive, negative on the bottom, that's negative. So overall, that interval is negative. For x equals 0, negative, positive, so that's negative. Positive, negative, that's also negative, but overall, negative divided by negative is positive. You can see how these are alternating, and that usually happens, but not always, so don't get lazy and just always alternate, because there's some cases where it stays the same. For this interval 2.5, I'm going to get positive, positive on the top, 2.5 on the bottom, positive, negative. So overall, positive divided by negative is negative. And then finally, for the last interval, plug in x equals 4. You can see all 4 of them are going to be positive. So overall, positive. Okay, so I've got my boundaries. I've also got the sign of the function between the boundaries, or the intervals. And now I go back and remind myself, oh, I'm looking for positive values or zeros. Okay, so I can, now just to make this super clear, so the asymptotes would be open circles because the function is not defined at those values. Okay, so the first interval I can see is positive, that's what I want. So everything here up to that asymptote is positive. Between these two are zeros, -1 and 2, so everything between them and including those endpoints. And then finally, the last interval, which is positive, is over here. Okay, so greater than 3. So if I was to put my final conclusion, looking at my number line, I'm looking for this section, so that's -infinity up to -4, but not including. Then I've got -1 to 2, but including both, so I use the square bracket. And the final interval greater than -3, so 3 to positive infinity, not including the 3. So that would be my solution there. Okay, so hopefully this is, we've got 4 good examples here for solving equations and inequalities. So got some homework for you to practice here. So please do that, and see you in the next lesson. Take care.